Okay, so good morning, everyone, once again. So today I will speak about composition rule of inference and the Bandler-Kohout subproduct. This is a joint work with Michał Baczyński, and we are both from the University of Silesia in Katowice. I'll just move one thing. Okay. These rules of inference are quite standard rules that are used in approximate reasoning, and our goal in today's contribution is to compare them, and we will base on one of the most, I think, okay, here, one of the most popular reasoning schema, which is modus ponens. And actually, I will speak about generalized modus ponens. So maybe some of you know that it's based on a rule, a set of rules, if then. Here, actually, I have one rule. If X is A, then Y is B. As an addition, we have a fact that X is A prime. So we have some properties A, B, and A prime. And in this case, these properties A and A prime are slightly different. So our conclusion, we would like to get that Y is B prime. So this would be that the object Y has a property B prime, which is in our what we are expecting is that it would be very similar to B. And here A, B, and A prime and B prime are properties which are in this approach given by fuzzy sets. So A, B, and these are fuzzy sets. And as I said, I will speak about two rules of inference. So this is the composition rule of inference, which is the basic one, and the Bandler-Kohout subproduct. So the first one looks like here. So we have a function I, which is a fuzzy implication, and we have our input. So this is A prime of X. And to compute the values of B prime, we use such a supremum composition where T is a T norm. For the Bandler-Kohout subproduct, we have that this rule is not given by fuzzy implication, but this time a T norm or any other generalization of a classical conjunction. And this composition is based, maybe not, of course, composition, but this rule is based on infimum this time. And as you can see here, we have some functions, some fuzzy connectives. So I will just give some theoretical background for this, for these notions. Maybe not the next slide, but because firstly, I would like to once again tell you what is the goal of our work. So we would like to answer the question when it is better to use Bandler-Kohout subproduct or composition rule of inference, and what is this depend on. And we have some hypotheses that we stated in the beginning, because we thought that if the sets A and B, which are from the fuzzy rule if then, if they are similar, whatever right now it could mean, then the more our sets B and our output B prime are similar for composition rule of inference. But if A and B are less similar, then a B and B prime will be more similar for Bandler-Kohout subproduct. So these are our hypotheses, but you will see what we have obtained. So now some theoretical background for this, because as I said, I mentioned about T norms, or triangle norms. this is a function which is a generalization of conjunctions. So this is a function which is associative, commutative. It is not decreasing, or we can say increasing, with respect to each variable, and it has a neutral element 1. And according to this definition, we can distinguish, I would say, many different families of fuzzy, of t-norms. But here I would just like to give one characterization for some particular t-norms, because I will mention about them later. So if we have a t-norm which is continuous and Archimedean, then it has such a characterization that it could be given by such formula, where f is a generator of this function, and this is a continuous and strictly decreasing function with some border condition, as we can see here, that f of 1 is 0. Then any continuous Archimedean t-norm can be given by such formula. And also I mentioned about fuzzy implications. So again, fuzzy implication can be seen as a generalization of classical implications. So of course they have to satisfy those border conditions as any classical implications, but also they are non-increasing with respect to the first variable, and they are non-decreasing with respect to the second one. And again, for fuzzy implication, we can say about at least few families of fuzzy implications. But today I will just focus on one of them, which are residuated implications. Residuated implications are fuzzy implications which are generated by a t-norm. So if we would like to get an R implication, we take a subprium of such a set of t, where this capital T of xt is not greater than y. And that's how we can generate residual implications. So here I have some examples of such R implications. And these are very basic examples. As you can see, for example, we have a minimum t-norm. This t-norm generates the Gödel implication, which is given by this formula. And for example, product t-norm, which gives us a Gauguin implication. And of course, the first one in the first row, we have the Łukasiewicz t-norm and the Łukasiewicz implication. I think these examples, these functions are quite popular. Okay, so I said in the beginning, when I presented, when I was talking about our hypothesis, that we think that if A and B are, the more they are similar, then B and B prime are also similar. For first was for the rule of composition rule of inference. So what do I understand by the notion of that two fuzzy sets are similar? So for fuzzy sets, we can compare them using the notion of similarity. And this notion, actually, for different authors, it has different, I would say, different sets of properties. And here I have just the properties that are usually accepted as the most important. So we have that function S can be called a similarity if we have that for the whole universe, and the empty set, the value is 0. If we compare to the same set, the value is 1. Also, if we compare two sets, we have this symmetry, so it doesn't matter what is the order of comparing them. And again, very similar for we could say for the symmetry is the third one property. if we assume that our fuzzy sets are finite, we could say vectors, then if we will have any permutation of this set, so any permutation of our elements, then the values of these, the value of the function s has to be the same. And here I have two very basic examples of similarity function similarity measures. The first one is, as you can see, that if a fuzzy set is, both of them are empty, this is 1. In the other case, we sum up the minimal value of those values for any argument, and then we have the sum of the maximal values. And M2 function, which is given by such formula where AM, the capital AM, is an arithmetic mean. But this is how we can compare two fuzzy sets which are given on the same universe. As we can see here, we have f of x squared. So A and B are fuzzy sets from the same universe. However, if we compare A and B, what I was trying to do in the beginning, so where I had a fuzzy rule if then a set A and a set B can be from a different universe. In such a case, actually we are not able to use such definitions, but we constructed some functions that are a little bit similar for the similarity measures. So if we take that our two universes are of the same cardinality, then we can construct some functions which are in our opinion could be seen as a kind of a pseudo similarity measures. So the first one is N1, and the second one is N1, but one is as an upper index. So as you can see, we have again the same as before. We have this fraction with sum of minimum and maximal values with the sum of them, but we have here minimal and maximal values, and also we take all permutations that are available for the set for our vectors, right? And the second one is the same. Again, we have N2 and N2 with the upper index. However, we take again a minimal and a maximal values, possible values according to a last example, which was given here for this M2. So these, of course, now we cannot say about the symmetry. However, if we have that X is the same as Y, I mean these universes, of course we will have the symmetry as well. So some of the properties of similarity can be satisfied here as well. So what we have done after this theoretical introduction is that we made an experiment with an image, and we compared them if we with using two different rules. So we have an original image. So this is the image number 1, and we took one fuzzy rule, which I will present later. But in general, it's like if we have that pixel is, because we understand this image as a set of a pixel, so each pixel was considered as an input. So if a pixel is yellow, we would like to transform it to, for example, the more green one. So we would like to have it more green shades. And the same rule was applied for composition rule of inference and for the Bandler-Kohout subproduct. And the results are the following, as you can see here. So just looking at those images, we can say that image obtained from composition rule of inference is, I would say, quite similar for the original one, but the one that we obtained from Bandler-Kohout subproduct is, I would say, completely different. So as you can see, where there were some white color, we have here the black one. So that's why we had such a hypothesis that it's not that if pixels are if the antecedent of our fuzzy rule is not similar to the consequence, then it is not. It is better to use Bandler-Kohout subproduct, because in this case the antecedent and consequent were quite similar. But what we have also done, because this images are quite big, so it will be a big a large amount of pixels to present it on a charts, because this is what we have done. That's why we just took a little bit. We made a new image which is made of pieces of the original image, and it has more than 1,400 pixels, and that was the amount of our inputs. So what we have done also is we used two pairs of T-norm and fuzzy implication. The first one was product T-norm, and the second one was the Gauguin implication. And also the second pair is Łukasiewicz T-norm and Łukasiewicz implication. So this is the rule that I was mentioning about before. So if an input pixel is yellow, so it has such a color, then the output pixels is green, this shade of green that we have used. And the second case is if an input pixel is again yellow, then would like to change it to some blue or a purple color, something in between. So we might say that if we look at those pixels, in the first case, they are more similar than in the second one. Each pixel we understood as a vector which contains of 3 elements, 3 arguments, because we took those pixels from the model RGB. So that's why we could compare them, and we compare them using our new, let's say, pseudo similarity measures function. So for the case number 1, we have the following values of those similarities. So these are the values of those pixels if we would like to have it yellow, and this if we would like to have it this green color. So if we compared them, we obtain these values. So of course the first and the third are quite big values. So this is more than 9/10, but this minimal similarity is also not so bad. It's more than a half. So we could say that these pixels are quite similar to each other. And now on those charts, we have our results. So, as I said, we might say that in this case, set A and a set B, so this yellow pixel will be as a set A and the green one will be as a set B, are quite similar. And now, how is after some result, after taking each pixel from this figure 4, if we take each pixel as an input, we will obtain the following results. So I don't have here the images that we obtained from our new image, which was obtained from the parts of the original one. However, here, as you can see on those charts, we have a charts where we have the similarity of A and A prime. So this is the antecedent. So we can say the yellow pixel, and A prime, each pixel of this set. And we have a similarity, the values on this part are similarity of B and B prime. So B prime will be the output pixel, which is obtained from our rule of inference. And as you can see on the figure of number 5 and 6, no matter which function, which similarity function we use, it will be M1 and M2, we can say that if the similarity of A and A prime is growing, then the similarity of B and B prime is growing as well. So we might say that they are this similarity are directly proportional to each other. However, if we use Bandler-Kohout subproduct, the values are not so ordered as in the previous cases, because as you can see on figure 7 and on the figure 8, there are sometimes, we can say, different situation, but the general rule is according to this magenta line. This is the regression line. So we might say that they are inversely proportional. So if A and A prime in most cases are very similar, then we might say that in such case similarity of B and B prime, so our output would be smaller. Here I have very similar results. Maybe they are not so visible because this time we have the results for the second pair for the pair of Łukasiewicz-Tinor and Łukasiewicz implication, and this is actually the same. The results are very similar. And the second case here is where we have our second rule, where we might say that pixels, our input pixels, so our set A and B, are not so similar. So here the values of similarity or pseudo similarity are not so high, that we might say. The minimal values are about 3/10 and the maximal over 7/10. So here results are the following. Again, this is not what we have expected, because for composition rule of inference, so figure number 13 and 14, we again have the similar results. So we have again this directly proportional dependence. However, for Bandler-Kohout subproduct, again we might say something like inversely proportional behavior. And very similar results for the Łukasiewicz-Tinor and Łukasiewicz implication, except the last one, where we cannot say that for the function M2 we have inversely proportional behavior. It's actually a little bit more like this line is going up, so it's something in between directional and inversely maybe proportional behavior. So what is our observation for these results? So in most cases we can say that the similarity of B and B prime is directly proportional for the similarity of A and A prime for the composition rule of inference. However, The similarity of B and B prime is not always proportional to the similarity of A and A prime for Bandler-Kohout subproduct, and usually, not always, it is inversely proportional for this rule. As I said in the beginning, I talked about some theoretical background because we also have some how we have called that the theoretical justification for this fact. So this is a very partial, it's only partial justification because it will be given just for some particular cases. Because like I mentioned in the beginning about R implications, a pair of R implication and a T-norm, if this T-norm is left continuous, will satisfy such a equation. And this equation is, we can say, a kind of a generalization of the generalized modus ponens with some interpolativity property. So maybe I'll just skip the details. And we have the following proposition. If we have that our universe are all the same cardinality, we have a set A and A prime and B. And let's assume that those values, I mean, the difference between these values are epsilon. Here for X and X prime will be some delta I. And so these are kind of a similarity for us because, yeah, I know I need to finish. So I just want to say that in this case for Archimedean continuous T-norm with a convex generator, so these T-norms which I was talking about in the beginning, we can have some inequality. So the value of this, what is taken for what is needed to calculate the value for compositional rule of inference is can be bounded from both sides, and if those epsilons are like here A and C are small, then the values will be very close to yi. Okay, so in this moment I will stop and then actually finish my presentation because the most important fact was given here. These are our observations. So thank you very much for your attention. These are some propositions from literature. Thank you once again.